Hello everyone. Hope you are doing well. Welcome to the online platform Civil Technobricks. Guys, here we will tune for instantaneous decoding of conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today we will go through the core concept of raster and vector data analysis. So, what is meant by raster and what is meant by vector? Raster and vector are the two fundamental GIS data formats where we have to represent the spatial data efficiently based on application needs. So the raster uses pixels while vector uses geometric shapes for the working activity, which is nothing but a working principle of raster and vector. Raster suits continuous data where vector suits discrete features. Means the continuous data is, we can say that the raster data, and the discrete features or the tabulated data, we can say that the vector data. So raster for elevation models we can use in civil engineering, where vector for road networks or line patterns, which is more helpful in analysis like terrain modeling and network analysis. So the core analytical capabilities of GIS by comparing the raster and vector data analysis. In civil engineering, the choice of analysis models depending on the problem you are solving or the problem you are taking, whether it's high precision site layout or a broad environmental impact study, analysis, assessment, etc. This session will explore the mathematical logic behind the both raster and vector models. By the end of this session, you will able to decide which analytical approach is best suited for various civil engineering applications, from transportation planning to water resource management. The space, which is quantized into a regular grid of cells, which is also known as a tessellation, where the satellite image is converted into rows and columns based on some color coding system, and we can check the elevation at any cell or at any pixel by just the clicking on that cell. So the matrix of values is the structured format for that reality of raster data. Each cell holds a single Z value, which is the elevation, which is shown in the 245 meter. Means X length, Y width, and Z is the elevation, just like a elevation model. So this is more suitable for continuous data collection, just like rainfall data, temperature data, variation in temperature, or variation in elevations of buildings or any crop-like structure. Guys, moving towards the map algebra, which is the raster overlay concept, which is a key concept where cell by cell mathematical combination is compared by using two layer, three layer, or n number of layers. Or we can say that the combination of any two layers. Suppose soil layer is there, A, vegetation layer is B, output suitability A plus B. Just comparison of both layers. Means with respect to that layer, just a 2D plane, we can assign any point or any value for each and every cell with respect to its characteristics, and we can just compare the characteristics of soil at the same place, at the same ground control point, at on the vegetation layer. At the end, we can also compare both the layers for the sake of our interest. It is also known as the map algebra. While vector analysis is about objects and raster analysis is about surfaces. So the world is divided into a continuous grid of cells, and analysis is performed by comparing cell values across the layers. This is also known as the map algebra. In civil engineering, raster analysis is the gold standard for modeling continuous phenomena like rainfall, like runoff, like air pollution dispersion, then elevation changes, etc. So it is computationally faster for large areas, and it is the preferred method for regional planning and environmental modeling. So we can make the arithmetic operations with respect to some values assigned, with respect to some values assigned to the any type of layer or any type of ground control points, and we can check the advantages, or we can compare the conditions. So what is the main advantage is that simplicity for complex modeling. Moving towards the geometry with intelligence, vector topology, where vector data is in picture, the irregular shapes are converted, or we can say that the ground control points are used for the surveying method, where nodes are there, arcs are there, and vertices are there. With respect to the nodes, we can compare the ground control points, or we can take the reference points. Arcs are used to join the two nodes, and vertices are the points where the irregular polygons may be considered as a regular one, or we have to convert that irregular shape in the regular format so that vertices are used. So definition for the geometry with intelligence, or we can say that vector topology, is explicit definition of spatial relationship between the features. So what are the features assigned or incorporated with that irregular shape with respect to the adjacency, that is my neighbor, just like for example, then connectivity, that is are we linked together, and containment, that is what is inside, means which type of data is collected, then which type of data will be compared, and which type of data is available nearby. Likewise, the geometry of intelligence or vector topology we can check by using the key components, nodes, arcs, polygons, etc. So why it matters, or what is the importance of geometry of or vector topology is enables the network analysis and error detection. So we can detect the error so that we can move forward the neutralize that error. For example, ensuring polygons are closed. If polygons are not closed, then we have some error. So we have to ensure that the polygons must be closed. Nodes in public sense empathomeres, no node or line segments is duplicated in a topological model. So any node or any line segment is not be duplicated in a topological model. Here, vector topology is nothing but a terrain model. We can say that where topological activities or characteristics are checked with respect to their ephemeris, and that ephemeris are most important for the geometrical point of view, or we can say that the surveying point of view. This geometry is based on the coordinate system. For any civil engineer, vector analysis is the primary tool for network-based model or network-based problems, such as determining the shortest route, determining the shortest path for a construction supply chain, or analyzing the connectivity of a city's sewage system, because vector data maintains that a clear mathematical decision or clear mathematical definition of topography or topology. So highly efficient for calculating exact length, exact perimeter, and the areas of discrete objects like land parcels or land boundaries or building footprints. From raster to vector or vector to raster, data conversion, which is one of the most important phenomenon, that is data conversion. Okay. So raster to vector conversion, which is in three phases: input, process, and output. So raster to vector conversion transforms pixel into geometric features. Pixels into geometric features. So the objective behind the conversion is that to enhance data's usability and accuracy in GIS analysis. So the digitization or automated vectorization technique, which is a working principle behind that data conversion, which improves precision but may introduce some errors. So we have to neutralize that errors carefully, or we have to identify that errors carefully. In civil engineering point of view, if we have to convert the scan maps into editable formats, then we can use that conversion of raster to vector, which is most important for the land record digitization and infrastructure planning, where vectorization technique is most important to convert that raster data or that pixel data with respect to the algorithm. At the backend side, processes are there, which will be a thinking process which marks the actual center line, and that center line is the output, which is the vector data. The smooth continuous line which shows the actual path or alignment. After that, focusing towards lines to pixel means conversion of vector data to raster data or vector to raster conversion. The process of converting vector data into raster, which is an important operation in remote sensing and GIS for the any civil engineering project. Vector data represents features using precise points, lines, polygons, while raster data represents the information through grid-based pixels or cells. So the process shown is called as a rasterization. Process is shown as that called as rasterization, where continuous vector shapes are transformed into pixel-based raster cells. So in GIS software, this conversion is commonly required for spatial analysis, terrain modeling, and image processing applications. Pay attention, guys, to what center point rule, which states that a raster cell is filled only when the exact center point of that cell lies inside the vector feature. I repeat, with respect to the center point rule, which states that a raster cell is filled only when the exact center point of that line lies inside the vector feature. This rule determines how accurately the original shape is represented in raster format. In civil engineering, vector to raster conversion is widely used in land use mapping, watershed analysis, in hydrology, digital elevation modeling for urban mapping, road corridor analysis for highways to mega highways or expressways, in satellite image integration within remote sensing and GIS environments. Moving towards the engineering applications or the real world applications of that raster to vector conversion or vector to raster conversion, or both at the same time, just like the layer to layer overlay analysis. So important real world applications of remote sensing and GIS technologies in civil engineering, particularly in hydrology, cadastral mapping, infrastructure planning. This application helps engineers analyze spatial data efficiently for planning and decision making. Hydrology using raster data, where grid-based satellite and elevation data are used for flood modeling, watershed analysis, drainage patterns, identification of drainage, water resource management, and many more. Raster data is highly suitable for terrain and environmental analysis. Moving towards cadastral mapping, using vector data where land parcels, roads, property boundaries are represented using precise points, lines, and polygons. This method is widely used for land records, urban planning, taxation, and legal boundary management. Site selection using overlay analysis, where multiple GIS layers such as transportation network, land use, slope, soil, vegetation, environmental constraints, etc., are combined to identify the most suitable infrastructure location for any construction project. So overlay analysis helps civil engineers to optimize the placement of highways, demarcation of dam catchment, industrial corridors, industrial zone, residential layouts, utility networks, while minimizing environmental and economical impacts. Stay tuned, guys. Happy learning.